The Magnum Opus. The Magnum Opus on Cosmology, Consciousness, and the Unknown by David Ballou. Self-published edition. To all philosophers who seek to know the unknown. Author's note. This book is not a textbook. It is not a treatise on what is already known. It is instead a map of questions, a record of my attempt to wrestle with the greatest mysteries of existence. For years I have been haunted by the unknown. Not only the gaps in our science, but the silence between the equations, the horizons beyond what telescopes can see, the puzzles that philosophers argue but cannot resolve. What began as scattered notes and restless thoughts has grown into what you now hold, my magnum opus, a work that stretches across cosmology, physics, philosophy, and speculation. This book is not meant to give final answers. It is meant to trace possibilities. It moves from the birth of the universe to the birth of meaning, from black holes to consciousness, from quantum entanglement to the idea that reality itself might be a kind of logic or code. Along the way, I have tried to remain honest about what can be tested and what lies beyond science, where imagination and metaphysics take over. If you are a seeker of truth, of knowledge, of wonder, then this book is for you. I wrote it for those who look up at the night sky and feel not only curiosity, but longing. I wrote it for those who believe, as I do, that our task is not only to measure the cosmos, but to find our place within it. To the reader, take what follows as both science and story, as hypothesis and vision. Some of it may prove true, some may forever remain speculation, but the act of reaching, of daring to imagine, is itself part of what makes us human. May this book be a companion for your own search. David Ballou. Prologue. The Invitation to Infinity. The story of the universe is also the story of us. Before there were nations, before there were words, before there were even human beings to imagine them, there were the stars. The first humans to walk the earth raised their eyes at night and found patterns in the darkness. They drew animals and gods across the sky, telling stories not only about what they saw, but about themselves. Our myths were constellations. Our constellations were mirrors. The sky was never just above us. It was inside us, demanding to be interpreted. But we live in an age where the myths of old are being replaced by something stranger, more powerful, and more humbling than even our ancestors could have dreamed. We now know the universe has a history, a beginning, an unfolding, and perhaps a fate. This story stretches across nearly 14 billion years, from a hot, dense birth at the edge of time to the scattering of galaxies into the dark. It is a story of physics and chemistry, of quantum laws and cosmic expansion. And yet, in another sense, it is still mythic, because no matter how precise our instruments become, the cosmos remains a mirror. Its mysteries draw us into reflection not only about the universe itself, but about consciousness, meaning, and what it means for something to be real. This book is my attempt to chart a map of that mirror. It is not an atlas of certainties, nor a catalog of final answers. Instead, it is a living exploration, a magnum opus in the classical sense, a great work that is also unfinished. Its pages attempt to trace connections between cosmology, quantum physics, philosophy, and metaphysics, weaving them into a framework that is both rational and visionary. This is not a book about what we know. It is a book about what might be possible, and about how our ways of knowing shape the universe we claim to describe. From the smallest quanta of space-time to the unimaginable scales of the multiverse, the cosmos resists final explanation. Each discovery opens new questions. Black holes, once thought to be cosmic dead ends, now hint at pathways to new realities. The structure of space-time itself may be emergent, woven from entanglement like threads in a tapestry. Entirely new dimensions may lurk just beyond perception. And in the background of all this, lies the human mind, the one instrument through which the universe knows itself, raising the unsettling possibility that consciousness is not an accident in the cosmos, but a principle of it. This book is organized into parts that follow the arc of this investigation. We begin with the foundations of the known universe, the Big Bang, cosmic evolution, and the limits of physics as we currently understand them. We move then to the multiverse theories, in which our universe may be only one of many, each with its own laws and histories. From there, we descend into the heart of mystery, black holes, and their potential role as seeds of new universes. We rise into the mathematics of higher dimensions and string theory, asking whether our four-dimensional experience is but a shadow of a richer geometry. We then explore the delicate fabric of quantum fluctuations and entanglement, which may bind universes together into a vast cosmic web. The later chapters expand into philosophical cosmology, examining models where mathematics, logic, or consciousness itself become the foundation of reality. Finally, we consider the strengths and weaknesses of these views, distinguishing what may one day be tested from what remains speculative, yet no less important for our imagination of reality. A note about method. This is not an orthodox cosmology text, nor is it a work of pure philosophy. It is a hybrid, speculative, synthetic, and exploratory. Throughout, I will mark the difference between testable science and speculative horizons. The first anchors us to observation: cosmic microwave background radiation, gravitational waves, particle physics experiments. The second carries us beyond data, into visions that may never be proven, but which serve to stretch our models and expand our intellectual reach. Together, they form a two-part harmony. Without science, speculation drifts into fantasy. Without speculation, science ossifies into dogma. It is in the dialogue between them that new thought emerges. To read this book is to accept an invitation, not to answers, but to infinity. Infinity is not merely a number without end. It is a principle of openness, of always more to come. Every horizon, once reached, reveals another beyond it. The same is true of our attempts to understand reality. Each theory reveals its own limits, pointing beyond itself to a larger framework. The history of science is a series of expanding circles. This book attempts to sketch the next one. We do not know if the universe is finite or infinite, if it had a beginning or will have an end, if consciousness is an emergent property of matter, or the foundation of all things. We do not know if other universes exist, or if the laws of physics are necessary or contingent. We do not know whether the universe is a dream, a simulation, or a self-existing fact. But in asking these questions, in structuring them, in daring to imagine possible answers, we do something profoundly human, and perhaps profoundly cosmic. We participate in the unfolding of reality itself. The universe may be unfinished. This book certainly is. But both, I believe, are worth entering with wonder. Part 1. Foundations of the Known Universe. The universe has a history. That single sentence is one of the most astonishing discoveries in the human story. For most of recorded history, people believed the cosmos was eternal and unchanging, a static backdrop against which human dramas played out. Stars were thought to be fixed in crystalline spheres, and the heavens were imagined as eternal and incorruptible. It was only in the last century that we came to realize that the universe itself is not a stage, but a character, one that is dynamic, evolving, and perhaps destined for an ending as strange as its beginning. Modern cosmology begins with the Big Bang. The phrase, coined dismissively by Fred Hoyle in a radio broadcast in 1949, has come to signify the most widely accepted model for the origin of our observable universe. According to this model, roughly 13.8 billion years ago, the universe was in an unimaginably hot, dense state. The laws of physics as we currently know them break down as we approach this Planck epoch, the first sliver of time after the beginning, when quantum effects of gravity become dominant. From this opaque primordial flash, space and time themselves began to expand. The earliest moments remain beyond the reach of direct observation. We cannot look back into the Big Bang itself, because light could not yet travel freely. But what we can observe is the afterglow, the cosmic microwave background, CMB, a faint bath of radiation that fills all of space, discovered accidentally in 1965 by Penzias and Wilson. This radiation, stretched by cosmic expansion into microwaves, is the oldest light in the universe. It shows us the cosmos when it was only 380,000 years old, cooled enough for atoms to form and photons to stream freely. Like a fossilized ember, the CMB preserves information about the density fluctuations that would later grow into galaxies and clusters. Cosmology, however, is not just about beginnings, it is about trajectories. The universe has been expanding ever since its birth. Hubble's observation in 1929 that galaxies are receding from us, with velocity proportional to distance, was the first empirical evidence of expansion. More recently, we have learned that this expansion is not slowing under gravity's pull, but accelerating, driven by a mysterious, dark energy that makes up nearly 70% of the cosmos. This discovery, awarded the Nobel Prize in 2011, has transformed our understanding of cosmic fate. If the universe has a history, then it also has a future. The possibilities range from the austere to the catastrophic. In one scenario, the so-called heat death, the universe continues to expand forever, stars burn out, black holes evaporate, and matter decays into a thin soup of radiation. Time itself would persist, but there would be nothing left to measure it by. In another scenario, vacuum decay, our universe is metastable, perched in a false minimum of energy. A quantum tunneling event could trigger a bubble of true vacuum expanding at the speed of light, rewriting the laws of physics in its wake. Alternatively, if dark energy were to change sign, the expansion might halt and reverse, ending in a big crunch. Or it might increase without bound, tearing galaxies, stars, planets, and even atoms apart in a big rip. Each of these fates is consistent with current physics. Which one is true depends on the nature of dark energy, a mystery we have barely begun to probe. The arrow of time is bound up in this story. Why does time flow in one direction? Physics at the fundamental level is largely time-symmetric. The equations describing particle interactions work just as well backward as forward, yet our experience is irreversible. Entropy, the tendency of systems to move from order to disorder, provides one explanation. The universe began in an extraordinarily low entropy state, and ever since, entropy has been increasing. This thermodynamic arrow is mirrored in the cosmological arrow of expansion and the psychological arrow of memory. We remember the past, not the future, because the universe itself is structured asymmetrically in time. And yet, the simplicity of the Big Bang model conceals deep puzzles. Why is the universe so flat, meaning its geometry is so close to Euclidean? Why is the CMB so uniform, when widely separated regions should never have been in causal contact? Inflationary theory, first proposed in the 1980s, attempts to answer these questions. In this model, the universe underwent a burst of exponential expansion in the tiniest fraction of a second after its birth, stretching quantum fluctuations into the seeds of cosmic structure. Inflation not only explains flatness and uniformity, but also predicts a spectrum of primordial perturbations, predictions that have been borne out by CMB observations. And yet, inflation itself opens the door to a multiverse, where different regions of space-time may inflate differently, leading to bubbles with distinct properties. What began as a patch for cosmological puzzles has become a launchpad into speculation about infinite realities. These are the foundations of our known universe. They anchor us in observation. The CMB, galaxy redshifts, large-scale surveys, and supernova measurements. They bind us in theory, general relativity, quantum field theory, and statistical mechanics. And they open, inevitably, into mystery. The Planck epoch we cannot yet probe, the nature of dark energy we cannot yet explain, the fate of the cosmos we cannot yet determine. To stand in the middle of this narrative is to feel both grounded and adrift. We are grounded in the precision of science, in data so exact it can measure the universe's age to within a fraction of a percent. Yet we are adrift in the recognition that the most fundamental questions remain unanswered. Why this beginning? Why these laws? Why anything at all? To ask such questions is not to undermine cosmology, but to extend it. The known universe is our starting point. Beyond it lies the landscape of the possible. Other universes, other dimensions, other logics of reality. But before we set sail into those speculative seas, we must understand the shore on which we stand. That shore is the Big Bang and the unfolding cosmic timeline. A story, 13.8 billion years in the making, with chapters yet unwritten. Part 2. The multiverse landscape. The word universe once meant everything. It was singular by definition, the totality of space, time, matter, and law. To suggest there might be more than one was, until recently, almost nonsensical. And yet, as our theories have deepened, we have been led again and again to the possibility that the cosmos is larger, stranger, and more varied than this one observable bubble of reality. The multiverse is no longer just a flight of philosophical fancy. It has become a serious, if controversial, hypothesis at the frontiers of physics. The most basic multiverse is born from simple arithmetic. If space is infinite, then everything that can happen must happen somewhere. Our observable universe is finite. We can see only as far as light has had time to travel since the Big Bang, about 46 billion light years in every direction. But if space itself stretches on without end, then beyond our cosmic horizon there are regions forever unreachable to us, each with their own galaxies, stars, and histories. In an infinite expanse, even the improbable becomes inevitable. Somewhere there may be another Earth, another you, reading this same page. This is often called the Level 1 multiverse, and it emerges naturally if the cosmos is infinite in extent. The second possibility, the Level 2 multiverse, arises from inflationary theory. Inflation, the idea that the early universe underwent an exponential expansion, was first proposed to explain why the universe appears so flat and uniform. But inflation, once started, is difficult to stop everywhere at once. Instead, it continues eternally in some regions, spawning bubble universes where inflation ends locally and hot Big Bangs begin. Each bubble may have different values of fundamental constants, different particle content, even different dimensionality. In this view, our universe is just one bubble in an infinite foam, drifting among countless others. The laws of physics we observe may not be necessary, but contingent, local bylaws in a vast cosmic archipelago. A third possibility, the Level 3 multiverse, is born not from cosmology, but from quantum mechanics. In the 1950s, Hugh Everett proposed the many worlds interpretation of quantum theory, in which every quantum event causes a branching of reality. When a particle is measured, it does not collapse into a single state. Instead, the universe splits, with every outcome realized in a parallel branch. In this view, the multiverse is not spread out in space, but in possibility. Every decision, every roll of the dice, every quantum fluctuation spawns a new world. If inflation suggests that all physical laws are realized somewhere, Everett suggests that all outcomes are realized simultaneously. The most radical is the Level 4 multiverse, proposed by Max Tegmark, in which every consistent mathematical structure corresponds to a real universe. According to this view, reality is mathematics, and every possible equation is incarnated somewhere as a physical world. Our universe is simply one expression of logical consistency, no more privileged than any other. If true, this is a kind of cosmic democracy, where every coherent structure exists by virtue of being thinkable, Other variations extend these ideas. String theory suggests the possibility of higher dimensional brane worlds, where our universe is a membrane floating in a higher dimensional bulk. Collisions between branes may even generate big bangs in an eternal cycle of cosmic creation. Quantum gravity hints at a seething foam at the Planck scale, where tiny universes are constantly budding in and out of existence. Even the simulation hypothesis can be framed as a kind of multiverse, one in which realities are stacked in computational layers, each simulating another. The multiverse offers answers, but at a price. It explains why our universe appears fine-tuned for life. If there are countless universes with different laws, then some fraction will naturally permit complexity, and we find ourselves in one of those simply because we could not exist in the others. But the cost is testability. Most multiverse scenarios are, by construction, beyond direct observation. Other universes, if they exist, may lie forever beyond our horizon, causally disconnected from us. Critics argue that this makes the multiverse unscientific, a metaphysical indulgence dressed in physics clothing. And yet, the multiverse is not entirely beyond the reach of experiment. Some models suggest that bubble universes might collide, leaving imprints in the cosmic microwave background, subtle circular scars in the oldest light. Others suggest that gravity, unlike other forces, might leak into extra dimensions, producing measurable deviations in experiments. Quantum many-worlds interpretations could be tested indirectly by searching for inconsistencies in quantum probabilities, though no such evidence has been found. The simulation hypothesis, too, has been recast as a scientific question. Might we detect the pixelation of reality at the Planck scale, or constraints imposed by a finite computational substrate? The multiverse forces us to confront a philosophical tension. Are we willing to accept a model of reality that may never be fully testable, if it provides explanatory power? Or do we hold science to a stricter standard, one in which only the observable is real? Einstein once said that imagination is more important than knowledge, for knowledge is limited. The multiverse is a test of that principle. It expands the stage of reality beyond comprehension, yet leaves us wondering whether we have stepped outside the bounds of science altogether. Still, the idea has a peculiar inevitability. Every time we have thought the cosmos was bounded, by the horizon of the Earth, by the dome of stars, by the edge of the galaxy, we have discovered something beyond. It may be that the universe is once again inviting us to expand our frame of reference, to see our everything as part of a greater whole. Whether or not the multiverse exists, the very act of considering it stretches the imagination. And sometimes, that is the first step toward discovery. Part 3. The Black Hole. Frontier. Few objects in the cosmos embody mystery as powerfully as black holes. They are the most extreme predictions of Einstein's general relativity, where gravity becomes so strong that nothing, not even light, can escape. Once considered mathematical curiosities, black holes are now among the most empirically supported entities in astrophysics. We have heard them through gravitational waves, seen their shadows with radio telescopes, and traced their influence in the orbits of stars. And yet, despite their empirical reality, black holes remain paradoxes, doorways to the limits of physics and perhaps to other universes. The existence of black holes was first glimpsed in 1916 when Carl Schwarzschild discovered a solution to Einstein's equations describing a point of infinite density. For decades, these solutions were dismissed as physically meaningless. But in the latter half of the 20th century, evidence mounted that collapsed stars could indeed form such regions, and by now, black holes are central to our cosmic understanding. Stellar mass black holes form in the death throes of massive stars. Supermassive black holes, millions to billions of times the mass of the Sun, anchor the centers of galaxies, including our own Milky Way. We know they exist. The deeper question is, what are they? At first glance, black holes are cosmic prisons, swallowing all information about the matter that falls into them. But in the 1970s, Stephen Hawking and Jacob Bekenstein showed that black holes are not entirely black. They radiate, slowly evaporating through quantum effects. This insight revealed a deep connection between gravity, thermodynamics, and quantum mechanics. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This holographic relation hinted at something profound. The universe itself may be structured like a hologram, with information encoded on boundaries. But Hawking's discovery also sharpened the paradox. If black holes evaporate, what happens to the information they contain? Quantum mechanics forbids the destruction of information. General relativity seems to allow it. This conflict, the black hole information paradox, is one of the greatest unresolved problems in physics. Proposed resolutions include exotic ideas like firewalls at the horizon, subtle correlations in the Hawking radiation, or wormhole connections that preserve information in ways we do not yet fully grasp. Beyond paradox, black holes invite speculation about creation itself. Several physicists, including Lee Smolin, have proposed that black holes may act as cosmic seeds. In this view, the collapse of matter into a singularity may not end in destruction, but in rebirth, a bounce into a new universe on the other side. Just as stars give birth to heavy elements that seed future stars, black holes may give birth to universes that inherit certain physical constants. In this framework, universes could reproduce through black holes, with laws of physics that vary slightly each time. A kind of cosmological natural selection might then occur. Universes that produce many black holes generate more offspring, and so their laws become statistically favored. Our universe, rich in black holes, may be the product of this reproductive process. The idea stretches our imagination, but it is not pure fantasy. It connects black hole physics with cosmology, offering an explanation for fine-tuning without invoking an anthropic principle. It also situates black holes as bridges, not just ends, but beginnings. In some speculative models, the singularity at the heart of a black hole may be avoided altogether, replaced by a bounce mediated by quantum gravity. In others, black holes may be linked to wormholes, connecting distant regions of our universe or entirely separate ones. The ER-EPR conjecture, advanced by Juan Maldacena and Leonard Susskind, even suggests that entangled particles are connected by microscopic wormholes, and that black holes may be the macroscopic embodiment of this principle. In this view, space-time itself is woven from quantum entanglement, with black holes as the densest knots in the fabric. Observational astronomy is beginning to probe these frontiers. The Laser Interferometer. Gravitational Wave Observatory, LIGO, has recorded the space-time ripples of black hole collisions. The Event Horizon Telescope has imaged the silhouette of a supermassive black hole, showing the bending of light around its event horizon. Future instruments may detect the evaporation of small, primordial black holes left over from the Big Bang. These are empirical footholds in a domain that was once purely theoretical. Still, what lies beyond the horizon remains hidden, perhaps forever. By definition, we cannot see inside a black hole, but by following the mathematics and the clues offered by quantum theory, we may glimpse what black holes signify. Black holes occupy a strange duality. They are among the most certain and the most mysterious objects in science. They are real, yet their interiors are unknowable. They are endpoints of stellar collapse, yet may be the birthplaces of new universes. They challenge our deepest theories, yet offer the promise of unification. To study them is to stand at the edge of knowledge, peering into darkness, aware that the darkness may conceal not annihilation, but genesis. If black holes are indeed cosmic seeds, then every galaxy may be a garden. Each supermassive black hole could be the root of a universe, hidden within its depths. Perhaps our own universe was born from such a seed, collapsing in another reality and blooming into this one. If so, the cycle of creation is deeper than we ever imagined. A dance of collapse and rebirth, destruction and creation, horizons and infinities. In the black hole, the cosmos may reveal its most astonishing secret, that endings are beginnings in disguise. Part 4. Higher dimensions and hidden realities. When we look around, we perceive 3 dimensions of space: up and down, left and right, forward and backward, and one of time. These 4 dimensions feel sufficient for describing daily life, from the fall of an apple to the motion of planets. And yet, as physics has pressed deeper into the fundamental laws of nature, it has revealed that these familiar dimensions may be only a sliver of reality. Hidden dimensions may underlie the fabric of the cosmos, invisible to us but essential for unifying the laws of physics. The story begins with string theory, which emerged in the late 20th century as an attempt to reconcile quantum mechanics with gravity. In string theory, the fundamental building blocks of reality are not point particles, but one-dimensional strings, vibrating at different frequencies. Each vibration corresponds to a different particle. One mode might appear as an electron, another as a photon. This elegant idea solves certain mathematical inconsistencies that plague quantum gravity. But it comes with a radical requirement. The mathematics of string theory only works if the universe has more than 4 dimensions. Depending on the version, it requires 10 or 11. What happens to these extra dimensions? Why don't we see them? The answer lies in the concept of compactification. Extra dimensions may be curled up into spaces so tiny that they escape detection, like a garden hose viewed from far away. From a distance, it looks like a line, but up close, it has a circular thickness. These curled spaces are not arbitrary. They are highly complex geometric structures called Calabi-Yau manifolds, and their shape determines the laws of physics in the extended dimensions we do perceive. The values of particle masses, the strengths of forces, even the existence of families of matter, all may be shadows of the geometry of hidden dimensions. String theory evolved into M theory, which proposes 11 dimensions and suggests that strings themselves are manifestations of higher dimensional membranes, or brains. In this picture, our universe may be a 4-dimensional brain floating in a higher dimensional bulk. Gravity, unlike other forces, can leak into the bulk, which may explain why it appears so weak compared to electromagnetism or the nuclear forces. Other brains may exist parallel to ours, perhaps with their own universes, invisible but close in an unseen direction. In some models, collisions between brains create violent bursts of energy, Big Bang-like events that birth new universes. In this sense, our own cosmic beginning may have been not a singular creation, but the result of higher dimensional dynamics. The holographic principle, another profound insight, suggests that our 4-dimensional reality may be the projection of information stored on a lower dimensional boundary. Inspired by black hole thermodynamics, the idea gained precise form in the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. This correspondence demonstrates that a theory of gravity in a higher dimensional space can be mathematically equivalent to a quantum field theory without gravity on its boundary. In other words, the physics of a volume can be fully described by information encoded on its surface. This holographic duality has revolutionized theoretical physics, providing tools to explore quantum gravity in strongly coupled systems. More philosophically, it raises the possibility that what we experience as reality is a kind of projection, a shadow cast from a deeper order. What evidence might we find for these hidden dimensions? Particle accelerators like the Large Hadron Collider search for deviations in scattering patterns that could hint at extra dimensions. Experiments test the strength of gravity at short distances, looking for leakage into higher dimensions. Astronomical observations seek cosmic strings, defects in spacetime that may be relics of higher dimensional physics. None of these have yet yielded definitive proof, but the search continues, driven by the recognition that our current framework, the Standard Model plus general relativity, is incomplete. higher dimensional theories offer both unification and humility. They provide a framework in which the disparate forces of nature may be manifestations of a single underlying principle, revealed differently depending on perspective. But they also confront us with the possibility that the world we inhabit is only a thin slice of a grander structure, like a flatland embedded in a larger space. We may never perceive these dimensions directly, yet they may shape everything we know. Speculatively, one might imagine consciousness itself as a higher dimensional phenomenon, intersecting our four-dimensional brain but extending into unseen directions. Or one might consider that what we call the laws of physics are projections of a deeper mathematical reality, of which we see only the shadow. Hidden dimensions thus serve both as rigorous mathematical requirements and as metaphors for the unseen depths of reality. The history of science teaches that expanding our sense of scale often transforms our understanding. Once, Earth was the center of the cosmos. Then it was one planet among many. Then one star among billions in one galaxy among trillions. Perhaps we now stand at another threshold. Perhaps our four-dimensional universe is itself a local expression of something larger, something hidden, waiting for the right mathematics, or the right experiment, or the right conceptual leap to reveal itself. Part Phi: Fluctuations, Entanglement, and the Web of Universes. The story of the universe is a story of fluctuations. From the very beginning, the cosmos has been shaped by tiny departures from uniformity, infinitesimal variations in energy density that later blossomed into galaxies, stars, and planets. Without those primordial fluctuations, the universe would be a featureless expanse of radiation, sterile and lifeless. Structure, complexity, and ultimately consciousness are gifts of imperfection. The cosmic microwave background preserves a snapshot of these fluctuations. The faint modeling in its temperature map, measured with exquisite precision by satellites like COBE, WMAP, and Planck, reveals density variations of 1 part in 100,000. These tiny irregularities, stretched by inflation, provided the scaffolding on which gravity could act. Over billions of years, matter clumped, galaxies formed, stars ignited, and planets assembled. We are here because the universe was not perfectly smooth. But fluctuations are not only seeds of structure. At the quantum level, they are unavoidable. The vacuum of space, far from empty, seethes with virtual particles blinking in and out of existence. Heisenberg's uncertainty principle forbids absolute stillness. These quantum fluctuations are not mere noise. They are woven into the fabric of reality. They underlie radioactive decay, enable the Casimir effect, and, according to inflationary theory, set the initial conditions for the cosmos itself. If inflation is true, then every patch of the universe began as a quantum fluctuation stretched to cosmic scales. The largest structures in the universe, superclusters of galaxies, may ultimately trace their origin to the restless jitter of the quantum vacuum. Entanglement takes this strangeness further. When two particles interact and become entangled, their states are no longer independent. Measure one, and the other's outcome is instantly correlated no matter how far apart they travel. Einstein called it spooky action at a distance. But experiments have confirmed entanglement beyond doubt. It is not a curiosity of the laboratory, it is a fundamental feature of nature. What does entanglement mean at the cosmic level? Increasingly, physicists suspect that spacetime itself may emerge from entanglement. In holographic models, the connectivity of spacetime is mirrored by the entanglement structure of the underlying quantum state. Black holes, the densest entanglement objects, may even be stitched to one another by wormholes, as suggested by the ER-EPR conjecture. If this is true, then entanglement is not just a property within spacetime, but the thread from which spacetime is woven. Extending this idea further leads us to the possibility of entangled universes. If inflation gives rise to a multiverse of bubble universes, then quantum mechanics may entangle them, binding their states in ways that transcend separation. Just as particles in our universe exhibit correlations no matter the distance, entire universes might be correlated across the multiverse. This could have subtle implications for cosmological observations. Small deviations in the cosmic microwave background or unexpected alignments in large-scale structure might be the fingerprints of entanglement across universes. While speculative, the possibility that universes themselves are quantum objects reshapes the metaphysics of cosmology. Reality would not be a collection of isolated worlds, but a web of interdependence. Entanglement also reframes the problem of consciousness. The human mind, at its root, is a network of quantum systems. Though mainstream neuroscience explains cognition in classical terms, some theorists, Roger Penrose and Stuart Hameroff among them, have speculated that consciousness may be linked to quantum processes in the brain. Whether or not that specific claim is true, it remains striking that consciousness and cosmos alike may depend on entanglement as a principle of unity. The universe knows itself through entangled neurons, entangled atoms, entangled worlds. The marriage of fluctuations and entanglement hints at a profound unity. Fluctuations drive novelty. Entanglement enforces coherence. One gives rise to difference, the other to connection. Together, they may be the generative and binding principles of reality, the yin and yang of the quantum cosmos. Our universe may be one fluctuation among countless others, yet stitched into a larger fabric by entanglement. In this view, existence is not a collection of isolated things, but a network of relations, vibrating and interlinked, extending beyond our horizon into the infinite. The implications for cosmology are staggering. If fluctuations are the seeds of universes and entanglement the threads that bind them, then the multiverse is not an incoherent sprawl, but a woven tapestry. Each universe is a pattern, connected to others in ways we cannot yet fully perceive. The cosmos is not only vast but relational, an infinite web where meaning arises not from solitary existence, but from connection. Part 6. Philosophical Cosmology and Consciousness. Science and philosophy have always been uneasy companions. Science insists on observation and testability. Philosophy asks questions that sometimes lie beyond experiment. Yet at the edges of cosmology, the two inevitably converge. Questions of origin, of existence, of meaning. These are as much philosophical as they are physical. If the known universe is a shore and the multiverse an ocean, then philosophy is the compass that points us across waters we cannot yet sail. At the heart of this philosophical cosmology lies a radical question. What is the nature of reality itself? Our usual assumption is that reality is material, governed by physical laws, which science uncovers and describes. But even this assumption invites deeper questions. Why these laws? Why any laws at all? Why something rather than nothing? One response is the mathematical universe hypothesis, advanced by Max Tegmark and others, which suggests that mathematics is not merely a language for describing reality, but reality itself. In this view, every consistent mathematical structure exists as a universe. Ours is simply one among many, no more privileged than a Platonic form of a triangle. This radical ontological democracy strips existence of its mystery, replacing it with logical necessity. If it can be described mathematically without contradiction, it exists. The challenge, of course, is that such universes may be utterly disconnected from ours, leaving us with no way to confirm or deny their being. Another approach is simulation theory, popularized in both philosophy and popular culture. Nick Bostrom's simulation argument proposes that one of three possibilities must be true. Either civilizations never reach the point of running ancestor simulations, or they do but choose not to. Or they do, and we are almost certainly living in one. If advanced civilizations can simulate universes indistinguishable from their own, then the odds we are in the base reality become vanishingly small. this idea has profound implications. Our universe might be code, our physics the rules of a program, our consciousness emergent from computation. And yet, even if true, it merely pushes the question back: who built the simulator, and what lies beyond? More ancient is the idea that consciousness itself is primary. From Advaita Vedanta in India to Western idealism, philosophers have argued that mind is not a byproduct of matter, but the foundation of existence. In this framework, the universe does not give rise to consciousness. Consciousness gives rise to the universe. Physics becomes the study of patterns within consciousness, just as dreams obey their own internal logic. Some modern theorists, like Bernardo Kastrup, revive this monistic idealism, suggesting that what we call matter is simply the extrinsic appearance of deeper mental reality. Quantum mechanics, with its puzzling role for the observer, has often been invoked, sometimes loosely, sometimes rigorously, to suggest that consciousness and measurement are inseparable. Bridging these views is the notion of emergence. Perhaps consciousness is not fundamental, nor an illusion, but an emergent property of complex systems. Just as fluidity emerges from molecules of water, or temperature from statistical ensembles, so too might consciousness arise from networks of neurons. But emergence itself raises questions. Why should complexity give rise to subjective experience at all? Why does anything feel like something? This is the hard problem of consciousness, articulated by David Chalmers, and it sits unresolved at the intersection of physics, neuroscience, and philosophy. In the Magnum Opus framework, consciousness can be seen as a cosmic participant. It is not separate from the universe, but entangled with it, a mode of existence through which reality reflects upon itself. Whether consciousness is emergent or fundamental, it plays a role in shaping our models. Every theory of reality is also a theory of how consciousness apprehends it. This recursive loop, the universe giving rise to minds that imagine universes, is itself a kind of cosmological structure, a Mobius strip of being. Philosophical cosmology also invites us to consider epistemic humility, the limits of observation, the horizon of testability, the constraints of logic. All remind us that reality may transcend our categories. This is not a failure, but an opportunity. Just as science thrives on falsifiable hypotheses, philosophy thrives on the recognition of limits. By acknowledging what we cannot know, we carve the space for wonder. And yet, the philosophical dimension is not divorced from practice. Ideas like the simulation hypothesis, the mathematical universe, or consciousness as fundamental may not be directly testable, but they influence the way we think about science itself. They shift our questions. Instead of asking only, what are the laws of physics? We also ask why lawfulness at all. Instead of only, how does consciousness arise? We also ask, what role does consciousness play in the unfolding of reality? These questions may not yield empirical answers, but they shape the narratives by which humanity situates itself in the cosmos. To write cosmology without philosophy is to build a map without a legend. We may chart distances, but not meanings. To write philosophy without cosmology is to imagine without grounding. We may construct castles, but they float in air. Together, philosophy and cosmology form a double lens, one clarifying what can be known, the other opening what can be imagined. Part 7. Calc. Speculative Horizons and Cosmic Futures. Every scientific theory begins as speculation. Once the idea that Earth orbits the Sun was a radical hypothesis, dismissed as heresy. The notion that atoms exist was a philosophical guess long before it became experimental fact. Black holes, too, were once thought absurd, singularities that nature abhors. Today, they are imaged and measured. This history reminds us that speculation is not indulgence. It is the seed of discovery. Yet it also warns us that not all speculation bears fruit. Some ideas remain forever beyond verification, more poetry than physics. The challenge of cosmology is learning to walk this knife edge between science and imagination. The known universe gives us strong footing. The cosmic microwave background, gravitational waves, large-scale surveys, and particle accelerators have made the early universe a laboratory. Inflation, though not yet proven, has yielded predictions confirmed by observation. Dark matter is inferred by multiple lines of evidence. Black holes have moved from theoretical equations to astrophysical reality. These are pillars of tested science. Beyond them, horizons open. Dark energy, which drives cosmic acceleration, remains a mystery. Is it a cosmological constant, an intrinsic property of space-time? Or is it something dynamic, a new field we have yet to discover? The answer will determine the fate of the cosmos. Similarly, the nature of quantum gravity remains hidden. Loop quantum gravity, string theory, emergent space-time. Each offers glimpses, none complete. These are domains where theory is rich but experiment is poor, where speculation guides us until technology catches up. Further still lie the realms of the multiverse, higher dimensions, and cosmological natural selection. These hypotheses explain puzzles of fine-tuning, entropy, and origin, but may resist direct test forever. If other universes exist beyond our horizon, their detection may be impossible. If the laws of physics vary across a cosmic landscape, we may only ever know our local patch. Critics argue these ideas are metaphysics, not science. But even metaphysics has value, for it clarifies the boundary of what can be asked and answered. At the farthest edge, speculation blends with myth. The simulation hypothesis, the mathematical universe, and consciousness as fundamental offer visions that may never be empirically settled. They are not science in the strict sense, but they are not irrelevant. They shape our imagination, our sense of place, our metaphors of being. They are modern myths, stories that may or may not be true, but that orient us within the incomprehensible. What unites all these horizons is a sense of incompletion. Every theory points beyond itself. Every explanation opens new questions. The cosmos refuses closure. Perhaps this is its deepest truth, that reality is not a finished edifice but an unfolding process, one in which we participate. Our science, our philosophy, even our consciousness are themselves fluctuations in a greater becoming. The universe is not something we stand outside of. It is something we are inside, shaping and shaped by it. The future of cosmology is thus not only technological, but existential. We will build bigger telescopes, deeper surveys, more sensitive detectors. We may measure dark energy with precision, detect primordial gravitational waves, or glimpse signatures of new physics. But we will also confront the limits of observation, the horizons beyond which we cannot see. How we respond to those limits will define the philosophy of science in the coming centuries. Do we restrict ourselves to the testable, risking sterility? Or do we embrace speculation, risking fantasy? Perhaps the answer lies in balance, a science grounded in data but open to imagination, a philosophy humble before fact but bold before mystery. Cosmic futures are not only physical, but human. If the universe expands into darkness, then our fate may be to create meaning against the backdrop of silence. If new universes are born through black holes, then we may be midwives in a cosmic cycle. If consciousness is fundamental, then our awareness may be part of the universe's deepest architecture. If we are in a simulation, then our questions about reality are themselves part of the code. Each future is a mirror, reflecting our hopes, fears, and longing to belong. In the end, the speculative horizon is not an escape from reality, but an encounter with its depth. To imagine the future of the cosmos is to imagine the future of ourselves. We may never know the ultimate answers. But in asking the questions, we expand what it means to be human. The act of speculation is itself a kind of participation in the infinite. Epilogue. Standing at the shore of infinity, we are creatures caught between scales. On one side lies the immeasurable vastness of the cosmos, galaxies strewn across billions of light years, black holes swallowing suns, universes birthing other universes. On the other side lies the immeasurable intimacy of our own minds, the pulse of memory, the spark of awareness, the wonder that such vastness can be thought at all. To write cosmology is to stand at this threshold, between the infinite without and the infinite within. The Magnum Opus has traced a journey. We began with the Big Bang and the unfolding cosmic timeline, with the evidence etched into the oldest light. We crossed into the multiverse, where infinity branches into possibility. We descended into black holes, those paradoxical doorways of destruction and creation. We rose into higher dimensions, where unseen spaces and hidden laws may shape the world we know. We turned to quantum fluctuations and entanglement, the restless ground from which reality emerges. We confronted the philosophical horizons, mathematics as reality, reality as mind, mind as code. And we ended at the speculative edge, where science and imagination meet, where the future of cosmology is also the future of humanity. Each step revealed both clarity and mystery. Science grounds us in observation, in predictions confirmed to 12 decimal places. Philosophy reminds us of the limits of knowledge, the questions that persist even when the equations are solved. Together they form a dialogue across time, the physicist measuring, the philosopher questioning, the poet weaving meaning. To stand at this confluence is to recognize that the cosmos is not merely an object to be explained, but a story to be told. And what a story it is. 13.8 billion years ago, a fluctuation in the quantum foam gave rise to our universe. Stars burned and died, scattering elements that became planets, oceans, cells, and finally minds. Minds that now contemplate the foam itself. We are, as Carl Sagan once said, the cosmos made conscious. But consciousness does not merely reflect the universe. It participates in it. Our models, our metaphors, our very act of questioning. These are as much part of cosmic evolution as supernovae and black holes. The universe does not only expand in space, it expands in meaning. Perhaps we will never know the ultimate truth. Perhaps the multiverse is real, or perhaps ours is the only universe. Perhaps higher dimensions exist, or perhaps 4 is all there is. Perhaps we live in a simulation, or perhaps mathematics itself breathes as reality. But certainty is not the point. The point is the search, the dialogue, the flame of wonder that keeps humanity reaching beyond horizons. In that reaching lies our dignity. In that reaching lies our destiny. The final lesson of cosmology may not be about beginnings or endings, but about humility. We are not at the center of the universe, but neither are we irrelevant. We are participants in a cosmos both knowable and unknowable, finite and infinite, law-bound and mysterious. We are seeds of meaning in a vastness that may never yield its secret. And yet, by asking, by imagining, by building our magnum opus of thought, we make the universe luminous. So let this book be not an ending, but an invitation to scientists, to philosophers, to seekers of the unknown. Continue the exploration. Expand the map. Test the theories. Dream the possibilities. Let the dialogue of cosmos and consciousness continue. For in the end, we are all standing at the shore of infinity, watching the waves of universes, listening to the silence of horizons, and wondering what lies beyond. Acknowledgements. This book is more than paper and ink. It is the release of thoughts I have carried since I was young, questions that have haunted me since the 8th grade. For decades, these ideas lived in silence, circling in my mind like restless stars, until I finally gave them shape and voice here. I want to acknowledge all those who planted sparks along the way, the teachers who tolerated my impossible questions, the authors whose words lit fires I could not put out, and the scientists and philosophers, Hawking, Sagan, Penrose, Tegmark, and countless others, who reached into the abyss and pulled back fragments of the unknown. To my family and friends, thank you for walking with me even when I was lost in my own universes. Thank you for reminding me that, though the cosmos is infinite, the love we share is what makes the search worth it. To every seeker, dreamer, and restless soul who has stared into the night sky and whispered, "Why?" You are my true companions. This book belongs to you as much as it does to me. And finally, to the universe itself, vast, silent, terrifying, beautiful. Thank you for being the question I have never stopped asking. This is my gift back to the cosmos.